This is version Mansour, and I'll be solving exam 2. So for the first problem, as you can see, I multiplied my PID, and then for the first part, the hexadecimal number for this problem is this number. I switched it to binary, converted it. Please don't pay attention to the yellow highlight. I'll explain it later. After I turned it to binary, I chose for this one and I register T2, register A 00004. Why did I choose and I? And I stands for and immediate. And that's because I chose it to do a bitwise logical and with a constant. The 16-bit immediate is 0 extended to the left and combined with the constant for RS in a bitwise logical and operation, and the result is placed in RT. So what are those abbreviations? OP stands for operation encoding table for value, RS source register number, RT destination register number, and immediate is the format we're using. So for each part is the first part is 6-bit, second part is 5, the third part is 5, and the last part is 16. And this binary stands for the numbers. So for this problem, the last number is 4, and as well here, this binary number is equal to 4, and so forth for the rest. For the second part, this after converting it to my number right here, it became 12. So I switched it to binary, as you can see, and divided it. I chose PEQ, register T2, 0 and 0012. Why PEQ? It means branch on equal, and to compare RS and RT, I had to use it, then do a PC relative a conditional branch, which makes me need to use the PEQ. An 18-bit signed offset, the 16-bit offset field shifted left 2 bits is added to the address of the instruction following the branch, not the branch itself though, in the branch delay slot to form a PC effective target address. Also, a note that if the content of RS and RT are equal, branch to the effective target address after the instruction in the delay slot is executed. So for here, as you can see, I just put the same kind of table. PEQ under it is the first 6-bit, then 5-bit, then 5-bit, then 16-bit for the offset format. And that is it for the first problem. For the second problem, I kind of divided it. This is my table after I changed the numbers. First, I said from step 1 to 3, we need one set of instruction to read an instruction. And we will also need the energy and the clock cycles. And as you can see here, I added 4 plus 4 plus 4 equal 12, and 4 plus 12 plus 12 equal 28. And these values right there is in nanojoules and cycles. And then from step 4 to 6, the loop executes for the 4,999 plus 1, which is 5,000 iteration. Each iteration, there are 2 add instruction and 1 branch instruction, and the 1 branch instruction will consume for the energy 8 plus 8 plus 12, 28 joules, and clock cycle 2 plus 2 plus 16, 20 cycles. Now for step 7, it will ask for 1 instruction require 2 nanojoules and 12 cycles of CPU, and I got these all from my box right there, table. So the total energy required, it will be equal 12 plus 5,000 multiplied by 28 plus 2 equal for that number in nanojoules, and then total CPU cycle needed, it will be 28 plus the 5,000 by 20 plus 12, which will be that number in cycles. And again, I got the 12. I got the numbers used in the equation from the table, and I got the 28 and 20 from the previous equations we made. And then for the total time needed to process the program, it's the number of CPU cycles multiplied by clock cycle time. And as you can see, after I did the equation, and I got 33.31 multiplied by 10 to the negative 3 second. Finally, MIPS stands for million instruction per second. Since we have 3 instructions, set, read, read, then the 5,000 will be multiplied by 3 is from loop that repeats 5,000 times, and add branch, and 1 from write instruction. So the program consists of 3 plus 5,000 multiplied by 3 plus 1, which will give me that number, and executed in the seconds that we had, the milliseconds that we had above. So to get per second, we divided the instruction over the millisecond, and we got this number, instruction per second. So in MIPS, million instruction per second, it would be 0.45 and the rest of this number. And then energy consumed, we got the number we got from right here, the total energy required, and we divided it by the seconds that we have right here, and then we got 7 milliwatt. And then finally, the last thing is to divide the number we got right here, and divide it by the 7 that we just got right there, and we finally get this number as MIPS per milliwatt.